the relationship between Cohen's kappa and the accuracy of classifiers. The idea of Cohen's kappa is that we have two classifiers and we want to know how consistent they are in their strategies to classify. But if both classifiers are often accurate, they will also often come to the same predictions, so we need to calculate out this accuracy of the two classifiers. So in general, we have two classifiers. The accuracy of the first, the probability for a correct prediction, is P1, and the accuracy of the second classifier is P2. And we observe a probability of P++ that both are correct. And now Cohen's kappa is calculated like this. The expected overlap of these two classifiers, the expected probability that both are correct, is P1 times P2. The probability that both are incorrect is then 1 minus P1 times 1 minus P2. And we observed a probability of both being correct, P++, and P minus minus is for the probability of both being incorrect. And then kappa is computed by subtracting the expected from the observed consistency and then normalizing it so that kappa does not go beyond 1. So here's a simple example. If two classifiers are randomly guessing, their accuracies are 0.5 and 0.5. The expected overlap would then be that both are correct. 0.5 times 0.5 is 0.25, and then both incorrect, also 0.25, leading to an expected overlap of 0.5. And in this example, we exactly have this case that on the diagonal, we have an overall observed overlap of 0.5, leading to a kappa of 0. So since both classifiers are randomly guessing, there is no overlap in their strategy. However, even with an accuracy of only 50%, it could happen that both classifiers are very consistent. So if for each instance both classifiers are either correct or both classifiers are incorrect, they can still have an accuracy of 50% here, but it never happens that they kind of deviate. They will always be linked in the sense that both are correct or both are incorrect, and that would be kind of magically creating your consistency, and this consistency would result in a Cohen's kappa of 1. Okay. Another third example before we get to the relation between accuracy and Cohen's kappa, because right here at the first and second example we see that Cohen's kappa and the accuracy are somewhat independent to some degree, because here the accuracy is the same, but Cohen's kappa can vary a lot. Let's look at example 3, which talks about independent classifications, which means that the classifier 1 has an accuracy of P1 and classifier 2 has an accuracy of P2. And as you will notice here, I exactly created the situation that they agree in correct classifications with a probability of P1 times P2, which is exactly the independent case. And in these cases, Cohen's kappa is designed to give you a Cohen's kappa of 0 for any classification accuracies P1 and P2, for any combinations of these two. But now let's come to a situation where Cohen's kappa and accuracy are actually dependent and growing together with each other. And I call this example the mixed independent classifications. And the idea here is that we have some instances where the classifiers, both of them, classify independently with an accuracy of P, and some instances where they both independently randomly guess. So this is a combination of the third example and the first example. In the third and in the first, we both saw that Cohen's kappa was 0. So again, the third example, if they are just classifying independently with their individual accuracies P1 and P2, we expect a Cohen's kappa of 0, and in random guessing there also is a Cohen's kappa of 0. But here we introduced a structure that some of the instances are higher accuracy P and some of the instances are just randomly guessing. So we can put together this confusion matrix again. The accuracy of the first classifier will then be P plus 50% divided by 2. So this is the average. Sometimes they have an accuracy of P, sometimes they have an accuracy of randomly guessing 50%, and that will average to P plus 0.5 divided by 2. The same accuracy we put for the second classifier, so there it's symmetric. For the actually observed probability of both making the correct classification, we have to basically go to the two cases. So first of all, in half of the cases, we get the accuracy of P, which leads to an overlap of P squared. And in the other half of randomly guessing, we get the 25% as we saw in the first example. Now, if you run the numbers of calculating what the this expected overlap is, or the expected consistency, multiplying these marginal probabilities here, you will get to some value. We will basically skip these tedious rearrangements. But if you then calculate Cohen's kappa, you will find that Cohen's kappa now depends on the accuracy, which we call here P. So for an accuracy P of 50%, so basically they are either randomly guessing or they are randomly guessing, so it's always random guessing, we again find Cohen's kappa of 0. But if we increase the accuracy of this one higher accuracy independent classification, so in half of the cases they classify with an accuracy of 75%, we get a kappa that's larger than 0, and if we up the accuracy even further, the kappa also increases. So what happens here? Cohen's kappa is actually telling us that the classifiers become more consistent as this accuracy increases, because there is some consistencies. The classifiers both have the same strategy in classifying better in some instances and worse in the other instances. So this basically strategy of choosing one subset of the instances creates this consistency, and this consistency grows as the accuracy grows, because low accuracy would still mean randomly guessing overall. Higher accuracies would basically develop this consistency between the two classifiers. So even though Cohen's kappa corrects in some sense for the accuracy, it still depends on the accuracy if the two classifiers are using consistent strategies.